Oh, hello there. I guess we should try an algebra lesson, yes? Let's do it. So we are talking about natural base E. So again, this is 8.2 for those of you keeping track. And the last lesson, we learned about exponential growths and exponential decays. And remember, our bases were anywhere from in between in between 0 and 1 or higher than 1. So our decay would be like 1/2 or 1/3, and our growth would be anything greater than 1. So there's also this thing called natural base E. So we're going to learn a little bit more about that. So here we go. So they have a real world problem here, and it's dealing with a footbridge that is a simple suspension bridge. Not a bridge that I would get on, but the footbridge forms a catenary curve. So if you don't know, a catenary curve is if you take a string and the loop that it makes, if you hold it a little bit loose, I guess, is called a catenary curve. So you can make catenary arches, like St. Louis Arch, which is just this curve flipped on up, flipped on. Okay, well, my rope doesn't do that. But that's what they're talking about with a catenary curve. So a function that represents a catenary curve includes the constant e. So e is a constant. It is a number, and we're going to talk about kind of where it comes from a little bit later, but we can use it to kind of work with this suspension bridge that forms a catenary curve. What mathematical question can you ask about the situation? So we could ask things like, what is the formula of the bridge? How low does it droop? How long is it? Things like that. And what information would you need to know is that formula, right? That would tell us everything we need to know. So of course, they're going to give us the formula, and of course, it's going to have E in it. That's a crazy looking formula, but I mean, it's just basically E to a power, and then E to a negative power, where X represents the horizontal position in meters in relation to the center point of the bridge. So if you had your bridge like this is your lowest point. I want to say that X is how far away from that center point you are, whether it's positive or negative. So then from there, once we have that, we can figure out a whole bunch of stuff, because this is y, where this is a function models the height in W, or the height in meters. So again, if we start here, what is the height from the ground? What is the height from up here to the ground? This is the formula that would tell us all of those things. And so we could use a calculator, and we can graph it. We can figure all these things out. But let's jump right into it and learn a little bit more about E. The natural base E. So E is another number that we as mankind came up with. So similar to pi, pi is an irrational number, 3.14159, and it describes the relationship of a circle's circumference with its diameter. E is also a number that mankind came up with to help describe the physical world. So we notice that as a lot of things were growing exponentially, that the function E, or not the function, the number E came in very, very handy to describe these things. So in like economics, like profit charts, things like that, E is used a lot in calculus, as well as a lot of the other physical side of sciences, so physics, chemistry a little bit, So again, it's a number that we came up with, but it's a really important number, and that's why we're going over it now. So even if you don't particularly see how E is useful in your life right now, know that it's something that you will definitely be using, especially if you go into a STEM career field. If you don't go into a STEM career field, you'll still may see E in things like college algebra and stuff like that. But you're not going to need it in your day-to-day life. So anyway, we're going to graph and analyze the function f of x equals E of x. So they have this cute little chart here for us. And what they're actually doing, where'd my pencil go? There we go. Is the table shows the function 1 plus 1 over x to the power of x. So that is kind of the definition of E. So this ends up getting simplified into a number, but this is kind of where it comes from because we needed a way to describe some of these relationships. And so let's see here. We can look at our values of x, 1, 10, 100, 1,000, 10,000, so on and so forth. And you'll notice that it starts at x equals 1, f of x equals 2, 10, 2.5, 2.7, 2.7169, 2.7181. So it is getting closer and closer and closer to a decimal value of something like that. So I say something like that because that is still a rounded number. It is an irrational number similar to pi, so it goes on forever, but we call it E. It's a special irrational number similar to pi, but we call it E. So we can use a calculator. Let's see here, and it just wants us to fill out this table. So let's see here. I'm going to make my calculator a little bit smaller. How small can I make it? So we'll start with this. So I'm actually just going to use my y equals function because I think that'll be easier to make a table. So I'm going to go into y equals, figure out all this other stuff, and we're going to say y equals hang on, let's make this bigger so you can see it. Let's see, where is e? So right here, it's a second function, e to the x. So this ln stands for natural log, and then the opposite of a natural log is e to the x. Again, you'll learn more about that later. But for now, we're just going to use our second e to the x. We'll put our variable there, and so we can graph it. But what I really want to see is our table. This. And so what numbers do we need? Negative 2, 1, 0, 1, and 2. So let's just up. So I'm just going to write these numbers on the screen. 0.1353, 0.3679, 1, 2.7183, and then 2 is 7.3891. Go away, calculator. So our negative 1, except we already wrote down my negative 2. So then our negative 1 is going to be 0.367 ... So I'm intentionally not rounding because those ... dots mean that the number goes on. I don't know if that's the right thing to do for what the book wants, but whatever. E to the power of 0 is always 1. Anything to the power of 0 is always going to be 1. 2.714. dot, 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 7.389, dot, dot, dot. See if we got close or not. Yay! I'm not going to plot these points because we've got a graph down here that we can look at. So it is worth noting the value of E lies in between 2 and 3 on the number line. So how would you expect a graph f of x equals E of x to compare to the graphs of g of x, 2 to the x, and 3 to the x? So 2 to the x would be less than E to the x. 3 to the x would be greater than E to the x. So as x approaches positive infinity, f of x equals E of x will lie between those two functions. So here is the graph. You can see the same thing on your graphing calculator. That's not a graphing calculator, that's chemistry. So if we go over to our graph, we can even zoom in if we wanted to. So it should look pretty familiar, pretty similar to an exponential growth function. Go away, calculator. Thank you. So the graph of f of x is shown using a graphing calculator to graph f of e of x, g of 2 of x, h of 3 of x on the same coordinate grid. What do you notice about the graphs? Select all that apply. So I'm just going to imagine, because if we look at this graph right here with our e's, the 3 of x is going to be above it, the 2 of x is going to be below it. So the graphs will have the same domains. The graphs will have the same ranges. Graphs will have the same end behavior. The graphs all have asymptotes at y equals 0. All three graphs go through 0, 1. Yeah, I'll agree to that. The graph of f of e to x lies between the graphs of 2x and 3x. All of the points on the three graphs are identical. That's definitely wrong. So these are all the similarities that we have. All the points in the graph are not the same. And if you'd like to see that, we can show that real quick. So we've got y equals e to the x. We can do 2 to the power of x and 3 to the power of x. And we graph. There's our red, and there's our black. We have to zoom in a little bit to see, but that black is right on the upper edge, if you will. So use the graph of f of x equals e of x to identify the following key characteristics of the function. So our domain, all of our x values that we can possibly use, any x, all on the real number line. Our range is going to be from 0 to infinity, because remember it started at 0 and it asymptoted at 0. End behavior as x approaches negative infinity, y does not approach negative infinity. So it's going to be this one. X approaches negative infinity, y approaches 0. If x approaches positive infinity, y approaches positive infinity. Y-intercept is still at 0, 1. Horizontal asymptote is still at y equals 0. So these are all just general characteristics of the e to the x function. How these characteristics compare to the general graph, where b is greater than 1. The graphs are the same for these characteristics. I'm going to go with these are the same characteristics. They're not the same graphs. They're still going to have different points on them, but they have many of the similar characteristics. And just like our exponential growth and decay functions, we can transform these graphs by moving them up or down, left to right, or right to left, whatever, by using the similar methods that we used in the last lesson. So this is going to be a lot of the same over again. So hopefully it kind of continues to reinforce, but we are using e to the x now as opposed to a regular number. So we've got our general form, so we've got our parent function, f of x equals e to the x. This is our general form. So this is a times e to the x minus h plus k. That should all look vaguely familiar. Parent function, blah, 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 blah. So the same thing that we did last time still applies. So using the first reference point and the second reference point and the asymptote, you can either graph from a function or take a graph and make a function from it by using some of these relationships that we have. Notice, I'm sure you all heard me griping a little bit on the last homework assignment. This is a times e plus k as opposed to e plus k over a, which it wasn't wrong, I don't think, but it was confusing in the last lesson. So this one, I think, should be fine. So notice that these functions are identical to the exponent function seen in previous lesson, but in this case, b equals e, or the base is e. So that's one less thing we have to figure out, I guess. So then our example is graph g of x equals 1/2 e times to the power of x plus 5 minus 2, using reference points and the asymptote. So first things first, we can look at this equation and we can pull out our parameters. So remember our general form of the equation, g of x equals a times e to the x minus h plus k. Sorry, I ran out of room. So when we look at our function again, we can easily see that here's our a. So our a equals 1/2. Our k is -2. And then our h is a -5. Now notice that's a plus 5 in there, but our general formula has x minus h. So we have to add that that negative sign in, or the opposite. We have to do the opposite of that one right there. So we've got our parameters, and then with those we can go through and graph. Use the parameters to find the reference points and the asymptote. So the asymptote is the easy one. That's our k. K equals -2. Our asymptote is going to be y equals -2. Right there. So now, using this table that they gave us up at the top, so using this part, we can find our two reference points. So our first one is going to be h for our x, and then our y is going to be a plus k. So we're just going to plug those things in. Yeah, so h is going to be -5, a plus k is 1/2 plus -2, or -1/2. or negative 1 and 1/2, sorry. So then our second point, so we've got h plus 1, so that's going to be a negative 4. Then we have 1/2 e minus 2, and then we're good to go. So here's a good question. How do you graph the points such as negative 4, 1/2 e to the minus 2, e minus 2, whatever. So first of all, notice that the e is not raised to a power. You should note, or you should remember that if you don't have a power there, it is an assumed to be 1. So you can still shove it into the calculator. There's no way to do it without a calculator. I would say simplify the coordinates using 2.718 to approximate the value of e. You can do that, or you can put it into a calculator. I would usually just shove it into my calculator and using the e to the x button, but then putting 1 in for e to the x. So to show you that, it's like if I wanted to turn this into a decimal point, I'm going to write it on the screen real quick. So what I would do, I would first go back to this part, and we're going to have, parentheses are your friends. So 1/2, remember our e is right here, so second e to the x, notice how I don't have an exponent, so it is assumed to be 1, and then we're going to minus 2. So then we get a decimal point that we can plot or graph or whatever. I knew it was going to come back. I don't know why it's doing that, but it's coming back. So then we graph. We grab our 2 reference points. We know our asymptote, and then we approximate from there. Makes perfect sense, right? Is transforming f of x equals e to the x a special case of transforming an exponential function with base b? I don't think so. It's just normal. Okay, guess not. Yeah, but it's not a special case, but okay, so yeah, e is just a specific value for b. Totally agree with that. So I guess I misunderstood what they were looking for. We can create an equation for a transformation of f of x equals e of x. So we've got our parent function, and just like our last time, we can use our reference points to make an equation. So we are given this graph, asymptote, reference point, and we can use this information up here, or these relationships, to then figure out our actual equation. Almost dropped my super fancy pencil. So let's see here, what we got. I'm going to write down our first reference point, which is h a plus k, and then our second reference point, h plus 1, a times e plus k. So we'll be using that. So we've got our reference points. We've got our first one, which is right here. That's our first reference point because it's got a 3. And then we've got a 4, which is so our h and our h plus 1. So our reference points need to be 1x apart, at least for these functions. So use the asymptote to identify k. Our asymptote is at y equals 1, so therefore our k is equal to 1. Easy enough for that. Oops, I don't want to delete that. So k equals 1. Which of the following represents the relationship between k and the horizontal asymptote of the exponential function? The horizontal asymptote is y equals negative k. No, I would stick with y equals k. There you go. So use a reference point and k to find a and h. So we're using our first reference point, which was 3 1/2. They're reminding us 3 1/2. So that 3 1/2 is going to equal our h and a plus k. So we know our k equals 1. So now we know our h equals 3 because our 3 and our h. And we also know right here that a plus k is equal to 1/2. So we know k is being 1, so a is going to be equal to negative 1/2. So k was 1, I subtracted it to both sides. 1/2 minus 1 is a negative 1/2. So a equals negative 1/2. Let's see here, what else are we missing? Let's get rid of some of this stuff. And let's see, how do the coordinates of the reference point help you find h and a? We just did it. So we'll move on. Okay. What could your work look like if you used the second reference point instead of the first? As long as you realize that it was your second reference point, you would have your second reference point equals this one right there, and you will eventually get the same answers. So you would start with 4 equals h plus 1, minus 1 from both sides, you get 3 equals h. That's what we got. You'd start with all this stuff, and then we would do some algebra, and we would get a equals negative 1/2. So your e's would eventually cancel out. So now that we've got all that, though, we can write our equation. So remember, our general form for our equation was up here. So our g of x is equal to a times e x minus h plus k. So we know all of those. So our g of x is going to be equal to a, which is negative 1/2, e to the power of x minus h, which is 3, plus 1. Let's see what they got. There you go. So when you use the right equations, which I did not do in the last lesson, or I tried not to, it works pretty well. How can you use your understanding of transformations of the parent function to check your equation? Match each feature with the equation to the transformation it represents. So a is less than 0, so the parent function, it doesn't shift anything because of the a. Parent function still doesn't shift anything. Parent function undergoes a vertical compression by a factor of 1/2. Yeah, I'll go for that. Or is it this one? We'll see what some of the other ones say. So the absolute value of a equals 1/2. Yeah, so this one is a vertical compression by 1/2. A is being less than 0 is a negative, the parent function is reflected over the x-axis. My brain thought a less than 1, so that's why I was a little confused. So h equals 3, parent function shifts 3 units to the right, parent unit shifts 1 unit up. Yay! Of course, we need a real-world situation where we're going to use this, right? So archaeologists and paleontologists use these functions to help date fossils. So carbon-14 is a radioactive isotope of carbon that decays at an exponential rate. The percent of original carbon carbon-14 in the fossil after T years can be modeled by that, where T is the number of years after the specimen died. What is the decay rate of the function? What is the age of the fossil? So remember the rate of exponential decay from last lesson. It was something like the rate +1 if it was growth, and then the rate -1 if it was, or 1 minus the rate if it was decay. So in this case, we can look at the context and go, we're definitely not growing carbon-14. We're not getting more of it. It's getting less. So we are dealing with a decay. So if we know that a fossil contains 16% of its original carbon-14, we can use that information to figure out how old it is. So first they want us to find the value of R. So remember that the equation, we'll come back to that. So how is this form of the equation related to exponential decay formula? So the parent function for the exponential decay is b to the power of x, where b is in between 0 and 1. So since e to the negative that number is 0.999988, whatever, it is exponential decay because that is less than 1. Yay! So then we set the base of the equation, the base of the function equal to the base of the exponential decay formula to solve for r. So this is what I was talking about earlier. So we set this equal to the 1 minus r. So then we just algebra, and then we can get this number right here. But remember, this is a percent. So when we actually write, the decay rate is about 0.012%. We have to move that decimal point 2 over. So that's why it's 0.012 and not 0.00012%. So just kind of keep track of that. So that was just kind of the rate of decay. Paleontologists aren't really going to pay attention to that. They do care how fast something is decaying, but they really want to know how old the fossil is. So that's what I'm going to focus on. So we would have to use a graphing calculator to graph the function. So I'll go ahead and graph that. They had kind of a clever idea here. They're going to graph y equals 16, or a line on n equals 16, and this thing to see where they intersect. So let me show you how to do that on the calculator. 1, 2, 3 zeros, 12t, and then I'm just going to write y equals 16 to remind me to do that one. So here we go. We're going to go to our y equals. We're going to put in our first one, 100 second e to the power of negative 0.00012x, and then y equals 16. So we look at the graph of that. There's our y equals 16, but like our exponential decay function is not even on the screen. So I usually just kind of zoom out until I can actually see something. Okay, so we see this. That's our exponential decay, and over here somewhere, I assume it comes up. There it goes. So here it comes down, and then it's going to do an exponential decay until it eventually crosses that red line. But this is going to be really challenging to figure out and figure out where it actually crosses. So there's a way to make your calculator do that, but you at least have to get close. So let's play with our window here, and let's think things through. So each one of these helps us deal with our window that we're looking at. So like our window, our x minimum, we don't need negative numbers in our x, so we can set that equal to 0. Our x maximum, we'll just leave it like that for now, I guess. I don't know. Our x scale, we can change that too. Our y minimum, again, we don't need negatives. So let's start and see what that does to our graph. Okay, so it doesn't, all my graphs are right there, so I'm way too high. I want to see more of the y. I need to zoom in for that. So our y maximum is probably much too high. So we'll just, I don't know, start something like that. Okay, still not helping us. I don't know. Oh, so when we think about it, let's think about it. We want to be able to see y equals 16. So having this maximum be so huge is not helpful. So we could just change that to 20 and put y equals 16 more or less in the middle of the screen. Hey, now we're talking. So we can see our y equals 16 line, and this is our exponential growth, I'm sorry, exponential decay, and it does cross at some point. And so now we can go over here to calculate, right there. So second, calculate, intersect, I think we'll do it. So our first curve, our second curve, bam. So our intersection is x equals this number. So I'm going to go ahead and write that on the screen. 1, 5, 2, 7, we'll round that up to 2. And that would be our t number. So that equals t. So how does the line n equals 16 help you find the age of the fossil? We had talked about, where did that 16? Oh yeah, so there was 16% left over. And so when does this function totally equal 16? 16? And that's where we got that from. So then our t is going to be that number, which is the same thing we got, except we rounded it. So the intersection point represents that after 16, nope. The intersection point represents after that many years, there is 16% of carbon-14 remaining. And there we go. So we have successfully dated that fossil.